Right, hello and welcome back everybody. Moving on to section 0.3, complex arithmetic and operations. This mathematical word complex, it really means a combination of real and imaginary. I'll write that down. Combination of real, as in our real numbers like 1, 2, 3, pi, 5 halves, negative 23.8, and so on. So it's a combination of real and imaginary numbers. And I want to spend a little bit of time just explaining why imaginary numbers are not actually imaginary, they're just as real as the real numbers. Maybe they're less tangible than the whole numbers, but they're close to equally as tangible as negative numbers and irrational numbers. So they're really not too crazy, these imaginary numbers. So I'm starting with this remark here where I basically say the math to English translation of multiplication by I. So I'm not describing I itself, but rather the act of multiplying by I. It's the same way you think about the act of multiplying by 2 is to double something. 2 is not itself doubling something, but the act of multiplying by 2 is doubling something. So that's what we're going on with multiplying by I. So there's some action that occurs. And when you multiply by I, you should really think about the English translation as rotating one counterclockwise quarter turn around some origin. I'm calling it 0, but give yourself a place you're going to rotate around. And you go counterclockwise one quarter turn. That is what multiplication by I means. The same way multiplying by 2 means to double something. Multiplication by I just means this quarter turn rotation. And once you establish that fact, adding I actually makes a lot of sense because you can adding I is really adding 1 times I, right? So you're adding 1 unit in the direction of a quarter turn, a counterclockwise quarter turn. So just think about stepping 1 unit in the direction, which is 1 counterclockwise quarter turn from the positive real number. So wherever you define your forward direction, positive direction to be, you're not stepping 1 unit in that positive forward direction. You're also not stepping 1 unit in the backwards direction, right? Because I is not negative. You're stepping really 1 unit to the left. So if you look forward, you would step 1 unit forward, but instead you're going to step 1 unit to the left if you're adding I to where you're standing. So that's really what the number I means. You can just think about it as this action of being kind of to the left of where you're currently facing by 1 unit. And the devil's advocate may still be a little bit mad at those descriptions and argue that you can have 3.75, even root 2 slices of pizza. Now, I would argue you can't actually have root 2 slices of pizza. I think quantum mechanics forbids that. But the other, you can't actually have a perfect amount of pizza anyway. Like you would never be able to measure it perfectly. But then somebody would say, you can't have I slices of pizza. And I kind of agree with you, but that's not all numbers do. They don't just quantify positive quantities, right? They represent actions in the world that aren't necessarily positive quantities. So like negative numbers work great in accounting for describing a balance, or even they work really great when you're trying to talk about distances. You can talk about a negative distance as being a distance in the opposite direction from where you were originally measuring a distance. So, you have to force yourself into a two-dimensional world for the number I to be kind of a real number. But once you admit that two-dimensional spaces exist, then the number I is just as real as any other number. So let's define, for now, the imaginary numbers, and this is slightly different than the complex number. The imaginary numbers are the purely imaginary numbers, and we've already talked about I in its translation, but the way it's mathematically defined, and I think a lot of you have seen this before, is just that I squared is equal to -1. I do want to comment that it's a number which satisfies this property, not the number which satisfies the property, because something like -I would also satisfy that negative I squared is -1, because the two negatives cancel, but there's still an I squared sitting around, so just one extra copy of a negative. But we also have something called quaternions, which we won't get to in this text, and actually most undergraduate mathematical courses will not get into the quaternions, except the quaternions do include other numbers, j and k, which also both satisfy being equal to -1 when they're squared. So if you're interested, if that sounds cool, look up the quaternions and you can learn a little more about them. But once we've established a single I, that's all we need. We need at least one of these objects which has the square equal to -1. Then we define the imaginary numbers as just the multiplication of the real numbers by this imaginary unit I. So you can really think about it, because the imaginary unit is, when you multiply by it, is this notion of rotating one counterclockwise quarter turn around 0. If you start with the real numbers, which we always like to write out as a real number line, there's my real numbers. If I multiply those real numbers by I, I'm going to grab the whole thing, maybe put 0 right there. I'm going to rotate the entire real numbers by this 1 quarter turn, and then I've got my imaginary numbers, which is like this number line that's pointing in the other direction, up and down. And so that's actually this object that I've drawn here is called the complex plane, and we'll see what that object looks like right now. So we have something called the Cartesian complex numbers, and you could get away and get rid of this word Cartesian and just call them the complex numbers if you want to, but I'm going to describe what this word Cartesian means when we're referring to number systems, or perhaps plotting systems, coordinate systems, because we will experience something else called a polar coordinate system very soon, and they kind of play, they're two sides of the same coin, Cartesian and polar system. So Cartesian complex numbers, or even coordinate systems, these are the cases where we have two axes which are 90 degrees or perpendicular to one another, and trace out all of space. Okay, so this word Cartesian is a result of René Descartes, right? René Descartes, and all of the French people are rolling in their graves with my pronunciation of that. But yeah, we've got René Descartes here, and he developed the coordinate system. I think the anecdotal story is that he was watching a fly around in his room and figured out that with a forward, backward, left, right, and up, down coordinates, he could perfectly map the placement of the fly. So that's the anecdotal story of it. And so we have this thing called Cartesian because forward, backward, left, right, and up, down are all 90 degrees to one another. They're perpendicular axes. And so any sort of plotting system where we talk about axes being perpendicular to one another, that's known as Cartesian plotting systems. So if we look at, and I'm jumping away from complex numbers really for just like 2 minutes. If we just look at a two-dimensional space, which is kind of our generic plotting space, two-dimensional plotting space, xy plane, there's my x and there's my y, and this is a two-dimensional plane. If we want to plot some Cartesian points in this plane, maybe I've got my example of 1, 1 over here, negative 2 pi, negative 2, and root 3, negative 5.5. So if I'm going to plot the point 1, 1, what I'm thinking about this point is that this first one means right by 1 unit, and the second one means up by 1 unit. So if I start at the origin, I go to the right by 1 unit, and then I go up by 1 unit. Where I end up, I call this point 1, 1. And then I would repeat that for my second point, negative 2 pi, negative 2, where I'm moving to the right, but that's maybe in quotes, because it's negative, I'm moving to the right by negative 2 pi units. So that's really to the left by 2 pi, or about 6.28. So I'm moving to the left by 6.28 units, and then I'm moving up by negative 2 units, which is really down by 2 units. So this is what I would call the point negative 2 pi, negative 2, and then finally, maybe my last point, root 3, negative 5.5, I'm going to be moving to the right by root 3, which is about 1.7. So we'll go maybe 1.7 units to the right, about right there. And then I'm going to go up, but in quotes, so it's really down because it's negative 5.5 units. We're going to go negative all the way to 5.5. And now we're here at root 3, negative 5.5. And so that's how we interpret the Cartesian coordinate system. I feel like if you haven't been exposed to other coordinate systems, you may be asking, is there any other way to interpret these? The answer is yes, we'll get there eventually. But for now, this should feel familiar. We're just going to give it the extra name Cartesian rather than just, the XY plane that you've always been used to. So we give it the name Cartesian. Here I actually have plotted in the text the actual thing that I just described to you one by one. So the Cartesian complex numbers are going to be described rather than, my previous setting was just talking about two-dimensional points. Cartesian complex numbers, I have a real number x. This is where I'm saying x is an element of R. So I've got a real number x, and then I have an imaginary number iy, right, where y itself is just in R, but I've multiplied it by I. So I've got some amount of, because of this x term, this is moving right or left. And then when we think about the iy, right, we've talked about that already, I is going to rotate us exactly 90 degrees to the right left, and so now I'm moving up and or down, and this is precisely the Cartesian coordinate system we were just describing. And then I'll mention that these complex numbers are also called normal form complex numbers. This word Cartesian is often used to describe coordinate systems and not necessarily the numbers themselves. I like using it for both because in fact in a lot of Calculus 2 courses we introduce the Cartesian coordinates as opposed to the polar coordinates, and this is a nice introduction to those names. Anyway, these are called the complex numbers. We denote them with a C. And if we want to plot them in the XY plane, you'll notice what I've done here. I still have X on my right-left quote-unquote real axis. Think about these as R. And then up top, I actually, instead of having XY, I've rewritten that as IY. And so think about this as the imaginary number times R. And if we want to plot some points on here, I'm actually going to plot the exact same collection of points, but now I've written them as complex numbers. We can think about the first one as 1 plus I, where there's my origin. 1 is saying I'm moving 1 unit, keep in mind that's real, 1 unit in the real direction, and I units in technically the real direction, but then it's 1 unit in the imaginary direction. So 1 unit to the left of the positive real direction. Similarly, I've got my negative 2 pi minus 2i, and that's going to look the same, where I come out to negative 6.28 over here, and then down 2 units in the imaginary direction. And then my third one, root 3 minus 5.5i. Root 3 is still about 1.7, so I go 1.7 to the right and 5.5 down. And we end up there. And so these are 3 imaginary, complex points plotted in the complex plane. And this is how we can think about the complex numbers. It's just like this plane of numbers rather than a line of numbers. What's slightly more important than even thinking about plotting these numbers is understanding that all of the operations we have on our real numbers actually still apply to the complex numbers. And that's what makes them quite useful. All of these operations means that we've just given ourselves an ability to work with more objects than we had before. So it just kind of opens the door to a brand new world of math that we can study, where all of the operations feel the same, but you have to treat them a little bit special. So if we want to add two complex numbers, all we're going to do is we're going to look at the real parts of each of them, and we're going to add those two real parts, and we're going to look at the imaginary parts of each of them. These are the terms against I, and we're going to add those two terms against I. If we want to subtract, it's a very similar idea. We're going to subtract the two real parts, and we're going to subtract the two imaginary parts from each other. The next two cases of multiplication and division are the tricky cases, so let's spend some time talking about those. In the multiplication case, you'll see on the left-hand side, this is just one complex number given here, and I've multiplied it by another complex number given there, but you get this really strange interaction in the output in terms of what is real and what is imaginary. You have these very strange interactions. I'm going to describe very quickly about where they come from. Let's think about, we've got a plus and a plus here as well as a times in the middle. What's actually happening is we're going to FOIL these. So if I go ahead and FOIL my terms here, I take the first two terms and I multiply them. That's going to give me x1, x2, which I do see on the right hand side. I'm going to take the outside terms, I'm going to multiply them. That's going to give me I, because there's an I here, x1, y2, and I've got an I, x1, y2 on the right hand side. If I look at the inside terms, I end up having an I from here, y1, x2, and I still have an I over here, y1, x2, the imaginary side. If I look at the outside, or the last terms, I get two copies of I, because both of them have i's against the y's. I get I squared, and keep in mind I squared is -1, so there's actually a -1 in front of the multiplication of y1 and y2. So that's where those multiplication terms come from, and the division term is even trickier than that. So we'll look at the right hand side of division here. I've got x1, x2 plus y1, y2 in the real part. That's been divided by x2 squared plus y2 squared, where those 2's are the terms in the denominator. And then in the imaginary part of x2, y1 minus x1, y2, and that's also been divided by x2 squared plus y2 squared. So it gets a little bit ugly, and the right way of seeing where this comes from is just in the proof that I've provided for you. So what we actually do to derive this is we start with the initial division, and then we grab that initial division term, and we're going to multiply it by the bottom. So there's the bottom, except I've flipped the plus sign to a minus sign in both of these terms that I've divided. This is called the complex conjugate. So I'll mention right here what we're doing is multiply the numerator and denominator by, it's called the complex conjugate, and we'll analyze that again later, complex conjugate of the denominator. And the only reason we do this is because in hindsight we know, and you'll see this later too, we know if we multiply something by its complex conjugate, it ends up giving us just each of the terms squared. So purely real terms. And once they're purely real, we can kind of factor them out of the I, which is what's important here. So we just go ahead, multiply the numerator and denominator by the complex conjugate of the denominator, and then we go ahead and actually perform some FOILings here. So first, outside, inside, and last, in both the numerator and denominator, and we go through a bunch of work and simplify. What we end up with is a numerator which has a real part here and an imaginary part here, and then a denominator which has ended up becoming purely real. But when it's purely real, we're just going to distribute that denominator to both terms in the numerator, and that's why it ends up in both sides of the denominator. And the I, that's right here, just comes along for the ride right there. And so it's back in normal form, right? Because that's a purely real term, and we have I times another purely real term. So a little bit tricky in that division. If you want, just go ahead and memorize what I've drawn in the proposition. So let's actually look at computing the operations on two complex numbers. So let's just give ourselves 1 minus I and a -3 plus 2I. If I'm going to add those together, recall, what do I do to add? I just take the two real parts, I'm going to add them. That's going to give me -2. I take the two imaginary parts. I've really got a -1 here for an imaginary part and a +2. So -1 plus 2 is a +1 on the imaginary part in the output. If I subtract, remember I'm just going to subtract the real part, so I've got a 1 minus -3, so minus -1 plus 3 should give me a 4, which I have, and then here I really have a -1 minus a +2, so -1 minus 2 is -3 in the imaginary term. If I want to multiply, let's just jump all the way back up here. If I want to multiply, I'm just going to take the two real terms, I'm going to multiply them together, and then I'm going to subtract the two imaginary terms multiplied together. That's going to give me the real portion of my multiplication. So if I look here, I have my real terms, 1 and -3, multiply together. I subtract the imaginary terms, which is really -1 and +2, and I'm going to multiply those two terms together. And then in terms of the imaginary output on multiplication, the imaginary output decides to take the second real term times the first imaginary term, as well as the first imaginary term times the second real term. And so these are really just cross terms. So I'll scroll back over here. What I'm looking at is cross terms of this real term times this imaginary term. So I've got a 2 times a 1, and I have this -1 imaginary term times this -3, which is going to be right there, -1 times -3. So then I just write those all out and I simplify, I end up with -1 plus 5i. And then if we want to look at dividing some complex numbers, if I go all the way back up here, let's think about what happened in dividing complex numbers. Well, we took the two real parts of the denominator, so that's the x2 and the y2, and we squared each of them. So the I did not come over in the squaring, it's just the two purely real numbers that are in the denominator. Those get squared. And so here we've got -3 and +2, which both get squared, and you'll end up with 9 plus 4, which will end up being 13. That'll end up in both denominators. And then let's go back and see what the numerators do. Well, the numerators, the first one is x1, x2 plus y1, y2. So that's the two real parts plus the two imaginary parts, where we have a 1 and -3 as our two real parts, and we have -1 and +2 as our two imaginary parts. So you go ahead and simplify that, you end up with -5, and then finally on the imaginary term, in the imaginary term, we've got kind of these cross terms, but they gain a minus sign, okay? So we have the cross terms with a minus sign. That means we have to be a little bit careful as to which cross term is on the left and which cross term is on the right, because the minus sign cares which term it's attached to. So in particular, it's the real part of denominator comes first. And then we have our cross terms with a minus sign. So if I jump back down here, I'm looking at the real part of the denominator, which comes first. That's going to have a cross term with the imaginary part of the numerator, so -3 times -1, as well as a minus sign, and then the real part of the numerator, 1, and the imaginary part of the denominator, 2. And if we simplify those, we just get a 1 in the numerator on the imaginary term. So next I'll remark that it's quite common to see in text that we will use z instead of the entire x plus iy term, because if we're kind of restricting things to variables, then it's just a lot of extra work to write x plus iy all the time when we just get away with a single variable that says, oh, this is a generic complex variable. So we'll start doing that where we just write z instead of x plus iy. And then we'll start describing some of these other definitions. There's something called a complex conjugate, which I referred to already. Sometimes this will just be called the conjugate. And it's denoted by a line above the number. So you'll put a line straight over the number. And you can do this over expressions like x plus iy as well. And it consists of taking every I and just putting it negative. So replace each I with minus I. And that's all the conjugate does. We're just going to find all of the i's and replace them with minus I. We'll look at an example. It's fairly straightforward. Let z be 1 minus I, and w, which is often the second complex variable, if we're going to work with two of them, be -3 plus 2i. If I take the conjugate of 1 minus I, I'm just going to take this I, and I'm going to make it negative, so I really have 1 minus -I, which will be 1 plus I. And then in w, we can do something similar, and I look at that I, or positive 2i on the end, I'm going to make that negative. That's all the complex conjugate does. The primary reason we have a complex conjugate is because it allows us to construct this norm, also known as magnitude. And before I describe how it gets produced, I'm just going to jump all the way back to when we were plotting these numbers. Like right here, we are plotting, 1 plus I, root 3 minus 5.5i, and -2 pi minus 2i. To talk about the magnitude, we're really asking the question of what is the distance to the origin? So magnitude, or norm, means straight line distance to the origin. And so that's just going to get computed with the Pythagorean theorem, because that is a right triangle, and it's got a width of 1 and a height of I, but the actual straight line distance of that height is just equal to 1. So we'll actually say that that's 1, and so this should be root 2. You just look at the 1, you square it, you look at the length on the I, and you square it, and you take a square root of that. That's the Pythagorean theorem for you. And that gives you that straight line distance, right? This is the same as your distance formula that you would have learned a little while ago. So that's what happens with these norms, and that's why you're going to see them as, the square root of a few things squared, because the Pythagorean theorem tells you that. And you can write it as, we write it as the absolute value sign. It's the square root of a number times its conjugate, but what that will reproduce is just the square root of each of the parts squared. Notice there is no I squared on the right-hand side. Right? We don't include this I when we're squaring it on the right-hand side for norms or magnitudes. You can only ever have positive numbers here. And if I had an I squared, it would make it negative. So we're only working with the x and the y itself, but you can also compute it as z times its conjugate. That's kind of why we have conjugates. They play the role of allowing us to get norms. So let's go ahead and look at how to calculate these norms. If we have z is 1 minus I and w is negative 3 plus 2i, well, then the norm on z, you can either calculate it as z times its conjugate, which I'll write as 1 plus I, and the conjugate of 1 plus I, which is 1 minus I. I realize I accidentally have the conjugate in the wrong spot there. But the conjugate is 1 minus I. And then if you FOIL that out, here's kind of me showing that the conjugate will always get rid of the i's, and you'll have a negative I squared, which is just positive 1. You'll definitely get that root 2 that you would expect from something like 1 minus I, right? If I plot this on the complex plane, 1 is this direction, minus I is in that direction, there I am. It's going to be the hypotenuse of that right triangle, which of course is the square root of 2. And then for w, you can do the same thing and take negative 3 plus 2i, as well as its conjugate, which would be a negative 3 minus 2i. So once again, I've got my conjugates in the wrong spot there. But the 6 i's in the middle are going to cancel because we've taken the conjugate. They're going to have opposite signs of one another, and you end up with root 13 in this case. But if you want to think about it the other way, let's just take the 1 and square it, and then there's a minus 1 here and I square it. What is 1 squared plus minus 1 squared? Well, that is 2. And then here you look at the negative 3, you square it. You look at the 2, you square it. What is the square root of 3 squared plus 2 squared? That's 9 plus 4, or root 13. So I wouldn't actually do it this way. I would just look at these two numbers and square them and add them together. We have something called the real and imaginary part, which I've kind of been referring to the entire time. It's just a kind of a projection onto the real or the imaginary part. You can think about it as a projection if you're plotting a specific point. Like here's my point. I can either project it down to be the real part there, or project it to the left to be the imaginary part there. It's just whatever number gets represented on the axes. You can calculate them in multiple ways. It makes a lot of sense to say the real part of x plus iy is simply x, and the imaginary part of x plus iy is just simply y. Now you don't include the I here on the imaginary part. We're asking about kind of like the magnitude of the imaginary part, so to speak. What is the real number which is attached to I? So you drop the I, but it's just that y term on the right. But we do have like algebraic expressions which can compute these, which are sometimes useful, and we'll see why these are useful later. So if you want an algebraic expression, you take a complex number plus its conjugate and divide by 2 to recover the real part, or a complex number minus its conjugate divided by 2i to recover the imaginary part. Now let's just see that would actually work with something like this. If I take x plus I y and I add it to its conjugate, x plus iy conjugate, and then I divide it by 2. What's that going to give me? Well, it's x plus iy, and then the conjugate is x, but then the conjugate makes the I negative, so x minus iy. These two iys are going to cancel each other because they're negatives of one another, and then I divide everything by 2. My numerator is just 2x, my denominator is 2, and I'm just left over with x. So that's why, the algebraic z plus z conjugate over 2 is the same as x. And then the same thing happens with the imaginary part. So let's actually calculate these. We have a few choices. With 1 minus I, what is the real part? You know right away it's just 1. And with negative 3 plus 2i, it's immediately negative 3. So like there it is, 1 and negative 3. But if you want to go through the work of calculating conjugates, adding them together, and then dividing by 2, you do indeed recover 1. And in the second case, if you do your conjugates and divide by 2, you do indeed recover 3. But don't overly complicate it if you don't have to. Same thing with the imaginary parts. Imaginary part of 1 minus I is just the coefficient on I, right? So the coefficient here is negative 1. There's my negative 1. The imaginary part of negative 3 plus 2i is the coefficient on I, which in this case is 2. And you can get away with this funky conjugate business here too if you want. You still get negative 1, and you still get 2. Okay, so we're going to stop there for today. I was debating whether or not to include the next section in today's video, but we're not going to do that. We're just going to keep a video alone to the polar complex numbers. And that's because kind of this idea of polar is the opposite, or it's a counterpart to Cartesian. And so I want to make sure we feel good about our complex numbers and Cartesian normal form complex numbers before we jump into this polar form. They're the same thing at the end of the day, but we should just take our time and really digest the first round of complex numbers before we get to the second round. Anyway, I'll see you in the next video. Thanks for sticking with me. Bye.